Now I think I should talk about the computational cost. So what is the computational cost of this depthwise separable convolution when compared to the standard convolution? So first of all, let me give you a recall of the computational cost in general. So in general, the computational cost is equal to the number of elements per kernel times the number of kernels times the number of positions taken per kernel, because the kernel should slide over the input, so at each so it takes different positions. So we are interested in the total number of positions taken per kernel. So this is the general formula of the computational cost, or rather the number of multiplications. I have talked about this in the previous video. And let's call the computational cost of standard convolution x1. So we have derived, the formula we derived for this in the previous video was df squared times dk squared times m times n. Now let's note the computational cost of the depthwise separable convolution as x2. So this should be equal to the number, or to the computational cost at this layer plus the computational cost at this layer. So the computational cost at this layer should be equal to what? So what is at this layer here, depthwise convolution, what is the number of elements per kernel? Well, the number of elements per kernel is dk times 1, which is dk squared. So it's dk squared. The total number of kernels is m, and the number of possible positions taken per kernel. So we should look at the input. We have an input of df times df width and height. Therefore, we should have here df times df, which is df squared. So this is the computational cost of this layer. We would do the same thing for this layer. So plus, so this is the computational cost of depthwise convolution. The computational cost of this layer should be, so the number of elements per kernel is 1 times m, which is just m. Number of kernels is n. And the number of possible positions per kernel, well, it's df times df, which is just df squared. So this is the computational cost of point-wise convolution. Now what's really interesting is not the derivation of this formula, but rather the comparison of this formula, or we want to figure out what is the reduction in the computation. So if you want to figure out this reduction, so the reduction in computations should be r, let's then denote it r. It should be x2 divided by x1. So you could get this in terms of percentages. If you want to know, just multiply by 100. But first we need to derive this, simplify this formula, because it could be simplified. So x2 divided by x1, let's work this thing out. So we would have this goes out with this goes out with this simplifies with this, so we get at the end dk, df, m, so we get 1 by n, right? So this is for the first term. This is this divided by this is 1 by n, plus this term divided by this term. So m goes out, n goes out, df, we get dk. 1 divided by dk squared. So this is the reduction. So let's compute this for a given configuration. Let's assume that n is equal to 32 and dk is equal to 3. So this is, by the way, a configuration that I took from the original paper of MobileNet V1 version 1. So if we replace by these numbers, then the reduction would be approximately 14.2%. So we should multiply this by 100 to get the percentage. What does that mean? So this means that the depthwise separable convolution takes only 14.2% of the computations required by the standard convolution. So to get a better idea about the computational gain we have, let's divide by r. So let's consider that t is equal to 1 divided by r. So this is equal approximately to 7. Well, it's 702, something like that, but just consider that it's 7. So this means that the depthwise separable convolution in this particular case is 7 times faster than the standard convolutions, which is quite useful. And so we get this computational gain while the accuracy reduction is very small. So it's something like the loss of accuracy is something like 1% to 2%. So it can goes up to 4%. So it depends upon the architecture you build using these depthwise separable convolution. But I think that in the original paper the maximum accuracy loss was 4% to the best of my knowledge. Now what's next? I think that the next point to cover is the computational. Well, this was why does it work? So there is, before understanding why does this depthwise separable convolution works well, that is why it does decrease the accuracy, it does decrease the computational cost versus a very small trade-off in accuracy. First we need to understand why the accuracy is expected to decrease. Well, in depthwise separable convolutions, the number of weights or parameters is smaller. So this means that the model complexity decreases. In other words, the accuracy is expected to decrease as well, right? The same thing applies for the standard convolutions. So in standard convolutions we have a higher number of parameters, the model's complexity increases, and therefore the accuracy is expected to increase, assuming that we are not overfitting, right? So this is in general. But there is one attractive property of depthwise separable convolution, which is this term, separable. So what does that mean? Well, in the original paper, the building block is not exactly like this. So they did not apply a pointwise convolution directly on the result of the depthwise convolution. Instead, they apply batch normalization plus ReLU. So let me just write it here, would be better. So what they do, so this is the depthwise separable convolutional block that is used in MobileNet V1 published in 2017. So this is what they do. They take the input f, right? They apply depthwise convolution. Then before applying the pointwise convolution, they perform a batch normalization. Then they apply a nonlinearity. They apply ReLU 6, I think. And well, I'm sure that it's ReLU, but which kind of ReLU, I'm not sure. I think it's ReLU 6. Then afterwards, after applying batch normalization in ReLU, they apply the pointwise convolution. And again, after the pointwise convolution, they apply batch normalization and then ReLU again. ReLU 6. So what's interesting here is that ReLU is applied twice instead of once. So in standard convolution, they just take the input f, they apply standard convolution, then they apply batch normalization, then they apply ReLU once. So here we have two ReLUs, the first ReLU and second ReLU, whereas in standard convolution we have only one ReLU. So when we apply nonlinearity 2 times, it means that the model's complexity increases. And when the model's complexity increases, the accuracy, of course, is expected to increase as well. So application of 2 times ReLU is kind of compensates this decrease in accuracy we have, but without increasing the number of parameters. And this is why it does, this is kind of the intuition why it does work so well. So I think that I went through all the main points I want to discuss in this video. But there is something else. Yes. There is an important question. So here, if you recall, I said that the 3-dimensional kernel is factorized or is separated into 2 kernels. The first kernel is this 2-dimensional and the second kernel is this, right? So why don't we separate or factorize this kernel into 2 smaller kernels as well? So we can, for example, factorize this kernel into a kernel that filters the height dimension,